All right. Evening, everyone. I'm going to maybe end a little early, like 5 minutes early. I have some quizzes I could pass back. If you want your quiz, just come down. I hand them out pretty efficiently. If you want to talk about the quiz, maybe about the problems, a bit more detail, I'll stay afterwards, and we can just, as a group, go over the problems. So I'll end maybe 5-10 minutes early. We'll see. Last time in class, we were discussing motion in 2 dimensions, and we started looking at projectiles, things that look like this, maybe. So this is an object that exhibits motion in both the horizontal plane and the vertical plane. So if we were to just sort of separate them so they're not connected at all, it would look like just this sort of A path, something moving only vertically, or something moving only horizontally. That's that path at the top, C. And that's sort of what I have a little demonstration up at the front, just to show this principle, that they are sort of, this cannonball, this green path that you see on the board. It exhibits both of these two, motions at the same time as something else that is only exhibiting one. So what I mean is, if I were to fire this cannon, the way it's arranged, and I was also to drop a regular cannonball right at the same time, they would both hit the ground at the same time. So that's kind of what this little thing I have up here at the front is going to show us. So imagine just the motion of something dropping. We all understand what that will look like already, and should just drop straight down. It's only exhibiting the vertical component of motion. And it's pretty, we could probably hear that. Maybe the recording can hear that even. But you can hear when it strikes the ground. Now, let me do just this one. Now this is going to throw the block that way. And it's going to have both components of motion. It'll be moving downward at a sort of predicted rate, and it will be moving to the side, this horizontal motion at the top. It's going to be moving that way until it's acted upon by something else. So, see the ones at the top? It's a constant horizontal velocity. It's also to check so that I don't hit the table. All right, so then I'm going to do both of them at the same time. So we have this one, going to have both components, and it's going to be sort of matched with this other equally sized cube, and you should be able to hear that they hit the ground at the exact same time. So that means that they both have the same vertical component. It's just this one over here has a little bit extra. It's doing a little bit more. It's moving that way as well. And this is something that can go on to, like extremes. Say I had an actual real cannon, or like a rifle, or some sort of firing range weapon, some sort. I can arrange this so it can go thousands of meters. It's starting out in a flat horizontal way, but I can also at the same moment drop like the same bullet. The same sort of bullet that is moving, and it's tested that they will also both hit the ground at the same time. Even though this one's going incredibly fast that way, it doesn't matter. They're both falling downward at the same rate. So the reason these are cubes is that we don't have to search for these for like an hour. Okay, I think that's good. I'll leave that set up. So that's kind of where we left off with these projectiles. I'm going to transition from projectiles into sort of things that may be in a different reference frame. What do I mean by that? I will show you. It's also called relative motion. So when maybe we're doing a problem, maybe we just want to think about physics when we're not in class, we can sort of do these problems, but we need to consider what is moving and what isn't moving. So that's sort of a very general statement. Who is the observer in your situation or your problem? Then you also need to consider, is the observer themselves moving? So most of the time, like in a problem or, for this example right here, you're all sitting still. You all have a velocity of 0 while you're sitting there. You see these things moving all over the place. Okay, you can tell it's moving. You know you guys are, at rest. But I think the easiest example is, did I put it on this frame? I put it on the next frame. Okay. So other times, maybe the reference frame is moving. Say, for instance, you are driving in traffic. You're driving on the freeway. You're going, I don't know, like 70 miles per hour. Other people are also going about that same speed. So if you look at the things in your car, you look at the steering wheel, you look at your water bottle, you say that's the water bottle, and the water bottle appears to not be moving. It has a velocity of 0 because it's in my reference frame. I'm in a moving reference frame. But say there's a pedestrian on the side of the road who also sees your water bottle. They can see it's moved past them in this sort of at rest reference frame. There we go. We can see this water bottle move past at, what did I say, 70 miles per hour. So we need to consider what is and isn't moving. This is sort of the little picture I had where you're in like a bus or something, and you can have like a ball or whatever. Your kids on the bus are tossing a ball around. Or someone's just like throwing a ball in the air like this. And they're in a bus that's moving. So to them, the ball is just going straight up and straight back down. All right? So to them, the ball is just going up and then back down. But to that observer on the sidewalk, the one that is really at rest, what they see is, they'll see the bus go by, however quick it's going, and they'll see the kid toss the ball up, and they'll see every moment of that ball's journey, it will sort of make this arc up and then back down. And so if you can sort of picture, if I had like a video of this exact example, it would be pretty easy. But say I'm moving at a constant speed. I throw the ball up in the air and I catch it. To you guys, you saw a parabola. To me, I only saw it going straight up, straight back down. This is sort of illuminated by this. It might not work that well. We have a, there we go. So I need to adjust this to make sure it's, so we have this little device. It's going to shoot the ball straight up, straight back down. Okay, I need to move it that way. Okay, maybe again. All right, it landed in. Okay, straight up, straight back down. It's not science unless it won't, unless it'll do it again. Okay, cool. So we know it goes straight up in the air, straight back down. I've also gone over with carts earlier that if I give it a little push, there's very little friction on this track. It does slow down and stop. But if I give it maybe enough like that, it's moving at constant velocity, more or less. So, as this constant velocity, it's a school bus moving along. And let's watch the kid throw the ball in the air. It landed in it. That's good. Let's try it again. Okay. So, we see that there can be multiple ways you can combine components. So, the kid on the bus, they're not throwing it at this arc. You guys saw the ball arc through the air, right? So the kid's not throwing it at an arc and then like somehow catching it themselves. They're just throwing it straight up, straight back down. So this is sort of the example that it doesn't have to be, a direct, toss at an angle. You can have these combination of vectors from different reference frames. Relative motion, yeah. Okay, what else? I think I was going to do a little example. We have like a small fishing boat that wants to cross a river. It's a very fast-moving river, and the boat can only go so fast. It's going to go at a constant speed of 10 meters per second. The river moving at 5 meters per second. This one, this problem needs a picture, so I will draw it. It also doesn't say how wide the river is, so the question is going to be very general. So there's our river. Everywhere in the river, it's moving at 5 meters per second. Let me actually make that. So I'm able to, might as well. The blue, and the boat is wanting to cross directly over the river. You go from one side to the other. So the boat is going to go, I'm just going to call it up. That's the way the boat's going. Velocity river. 5.0. Velocity of boats is 10.0. So maybe if you've sort of been in this sort of a scenario before, or even just looking at the picture, the boat is going to get carried sort of sideways, right? I'm sort of expecting that the boat, if it keeps going directly straight up, it's actually going to go that way, right? So the first question is, what is the, or how fast does the boat appear to be traveling from an observer on the shore? So if you ask the person in the boat, they say, I'm moving at 10 meters per second, because that's their own reference frame. But for someone on the shore, they see something different. They see that sort of sideways slanting angle, that speed. So how do we find this? This is just basic trigonometry now. We need to find the hypotenuse. Do like that. We just need to find the hypotenuse of that triangle. How do we do that? No one? Pythagorean theorem. All right, so it's just, finding the hypotenuse. I'm going to call this whoop. All right. It's as easy as that. If anyone has a calculator, that would be great. Let's see. So it's 125. 125, it's going to be around 11. 11.18. 11.18. Awesome. Significant figures. 1, 2. The lowest one in our question is 2. So that means I'm going to round this to 2 significant figures. So we'll just say 11. So they see, the observer on the shore, they see the boats moving faster than, the person in the boat feels like they're moving. This is a very general question on sort of like reference frames. Finding the angle, how far is this boat deflected? As soon as we learned all that trigonometry, we're just using it all the time. Okay, we're finding the angle, deflected. Now that we know all of the sides of the triangle.
Just a quick question. The 5 meters per second was because of the rate of the river, right?
Because the rate of the river is pushing it one way, right? Yes. Yeah. All right, basically we can use sine, cosine, we can use anything. So we know all the sides of this triangle now. Let's use tangent. So it would be 5 and 10. 5.0. That gives us inverse tangent of 1/2 or 0.5. Does anyone have that angle? Let me know when you do. All right. Thank you. Anyone got the angle?
26.5.
26.5 degrees. That means that the person in the boat has to travel more because they're getting deflected from where they originally wanted to go. So maybe questions on, how do you not be deflected? How do you counter that flow from the river? It's pushing you one way. So think about that for some of the homework, I believe. Okay. Next up, while we're still on like this reference frame or relative motion idea, I remembered from a while ago. I mentioned I like Mythbusters. In one of their episodes, they had this idea or this sort of thing they were testing. What they're doing is testing this idea of relative motion. In the back of this truck, they have a really huge cannon, and they're firing out a soccer ball. What they're doing is they perfectly timed sort of the power, escape velocity of that soccer ball, so that it's exactly 50 miles per hour. Then they put it in a truck, and then now they're driving at exactly 50 miles per hour the other way. So you have 50 that way, 50 that way, and what it appears to the observer, to us, is that the ball is just coming out and landing on the ground. It's nothing, no big deal. But then picture yourself sort of in the truck bed, firing this thing. You're seeing a ball fly out 50 miles per hour out of the cannon. So this is sort of the, this is like a big, I can't do this in the classroom. But it's sort of, on topic. I thought it was pretty cool. All right. What's next? So basically, we finished the chapter. Moving on to the next chapter of Newton's Newton's laws of motion. It's basically our introduction to forces. First, we need to sort of define forces, see what they are, and where they came from. They came from this guy right here. No, they didn't come from him. He sort of like defined everything. He made everything really nice for us to be able to learn it today. So, Isaac Newton was, let's see, he was sort of like revolutionary in the world of math and physics. In the, let's see, I think late 1600s, there was, I think it's just called like the London Plague or British Plague. And so everyone was advised to go home and quarantine. So he left school. He went home and he stayed there for, I forget how long, a couple months, maybe a year or two. And while at home, Isaac Newton, he was sort of like, that's sort of that story I told earlier, apple falling on his head, and he's like, things accelerate downward toward the ground. And I know everything does equally. You do little tests. And he saw the moon in the sky, and it sort of like stayed in his head constantly. He said, why isn't the moon crashing into Earth at 9.8 meters per second squared. So what he did, he's actively like mapped out where the moon was. You know, on the board when I was doing those position vectors, you know, one right after the other, right after the other. That's what he was doing all day. Quarantine. And he got super sick of it. I only did like 2 points for you guys. And it was already kind of too much. But he got to a point where he didn't like how he had to keep drawing out these lines, measuring, all this, you know, very tedious work. So in order to sort of like estimate everything, he sort of, you know, he saw that formal math form I kept showing you guys, the limits of something something goes to 0. He said, maybe I can take that a little further, maybe I can make my work a whole lot easier. And so he invented calculus, just to make his problem easier, solving this path of the moon. He also sort of, you know, while doing this, he had like very strict, you know, rules he would follow on motion, things that experience forces. So what he did, he sort of like saw that if I have something that's heavy and it's moving, you know, how does it change? How do I get it to start moving? How do I get it to stop moving? And he was able to sort of like sift through everything, and he found some very clear sets of rules, and that's what we're going to go over as the first, second, and third law. Just a second. So let me put some basics down right at the beginning. A force is a vector. Forces are vectors. So that means the direction is important. This is probably, you know, the most important thing, you know, of this first half of the semester, probably the whole semester. The direction of these forces are important. What else can I add here? Yeah, typically, since they're vectors, they are just labeled F. So that brings us to Newton's first law of motion. This is commonly just called the inertial law. Let me put up here. Law of inertia. So you gotta think this is sort of like devising a plan to sort of like start from the beginning. You know, we know a lot of this physics already. I'm sure a lot of you already sort of intuitively know a lot of things I've covered, but it's hard to sort of like break it back down to the beginning and start from scratch. So that's what he had to do. He first had to ask, what is mass? I told you guys about mass in the very first lecture. About a kilogram is SI unit. Newton had to ask the same thing. In general, what he came to was mass is a property of all matter. So doesn't know quite like how to, take it back to this step. So he's just sort of defining things at this point. So everything that has matter, this table, this tray, this metal scale, it's matter. It's a physical thing. It will have mass. What is inertia? I think before I define inertia, this is where I'll sort of state the law out in full up at the top. Newton's first law of motion states that an object at rest tends to stay at rest and an object in motion tends to stay in motion. Okay, and this is why he had to say, like, well, okay, what are objects? Well, objects have mass. Okay. Why do they sort of, things that are still like staying still, things that move like to move. As soon as I get that going, it seems like it wants to keep going. There are things slowing it down. There's friction. Imagine we're out in space or like a air hockey table. If I give it a push, it will just keep going. Why isn't this tray moving? That's sort of like, well, I have to get it to start moving. That's the thing that he was dealing with. What is inertia? That is masses. Let me write it. How should I phrase this? Masses, ability, no. Oh, that's better. Yeah, that's better. Masses, I can't, resistance? Resistance is the right word. Resistance to change. Oh my goodness. There we go. That's fine. So, things that have inertia resist change, whether it's while they're staying still or while they're moving. I have two things up here at the front. I have two cars up here. They look exactly the same. Let me scoot this back. So it has its own mass. It's matter. That means it has inertia. It wants to resist change. Right now, it is staying still. So it wants to stay that way. And I have this sort of like, I have this scale, measures force. Right? So this one is fairly light. So let's see if I can get this to show up. Maybe up to like 2, if you guys saw that. This one's fairly light though. This one over here, it looks exactly the same, but it has more mass. So that means it has more inertia. More inertia means more resistance to change. What does it go like to 8 or so? So I was kind of like over there. Was it like 6 or 7? Yeah. Okay. So it takes a lot more force to get it to go to start moving because it has more inertia. Okay. Newton's second law is one that will actually help us out when we are sort of doing work on like homework or experiments of any kind. Newton's second law is this sort of observance. I had this thing here. It's so much mass right here, and it took a certain amount of force to get it to start moving. So what Newton did, he sort of did this with several things, and he found this link between them all. He noticed that the amount of force that is required to get something to start accelerating, start changing its velocity, is related to the mass of the object times how much do you want it to start accelerating. So this is the famous force equals mass times acceleration. You'll use this almost forever in any physics class. It's also one of the easiest equations to remember. It's only 3 things. Something else I should say is that since in a lot of our situations, it's not just going to be, it's not just going to be something that's forcing it that way. We have to consider eventually other types of forces that might, oppose, or maybe it's also going up and down. We need to add up several forces together. So I'm also going to write this, or no, I'll put that up there. So what that means, that's just the summation sign. That means all of the forces. So force 1 plus force 2 plus force 3, however many I have. Also going to put this for any type of coordinate system we are using. So remember that when we are doing problems, we are splitting things up into only the horizontal bit, only the vertical bit. We need to also think about only horizontal forces. This would be the horizontal one. That looks a little wild. This is the vertical force. And it's just remembering that we're eventually going to have to start summing up forces that might be, maybe, I don't know, for like this example, I guess this is an easy example, is I'm pulling this way, pulling it that way. Someone else is also pushing it that way. 2 forces, both horizontal. I'm going to have to add that. So that's very easily done. That's just with that. Okay. Let's see. Newton's third law. I typed this one out beforehand. Okay. Every action has an equal and opposite reaction. So let's see. Let me. Okay. So, I can have a force. I could apply a force onto something. I could push. Maybe I could pull. What does this mean? Every action is an equal and opposite reaction. Well, consider this box right here. I'm placing it on the table. It's not moving, but there is, some forces at play here. So if I were to not have this on the table, where would it go? It would go down. It would accelerate downward. So this has a mass, and it is constantly accelerating downward. So that means it's applying a force downward onto the table. So let me draw that. Say the force of the box is down onto the table. So it's forcing downward. Why isn't the box just like going though? What's stopping it? What's stopping it from like busting through the table and like going down to the center of Earth? The table. The table has an equal force upward on the box. So this is the case with anything. Not just the box. I can sit on the table. I'm applying a force down on the table, but the table is forcing me up. It's keeping me here. Okay. I can start, pushing on things. I'm standing on the ground. I'm forcing, a small area on the ground. The ground is forcing me up. When we get into things that start to move, that becomes a different issue. I'll talk about that in the next slide. So, it's this case of things that are at rest. This box on the table, why isn't it moving? Is because there's a force upward holding it there. Why do things stay still at all? Why is that box not going? Well, that's because of the normal force. It's basically the same picture. The box. And I'm going to let's draw a dot right in the center. We're going to make what's called a free body diagram. So let's say I get sort of bored. I don't want to draw this box over and over again. Maybe it's like your problem is a car or a bike. So I'm going to draw the force that the box is applying to the table. It's down, and it's of a certain size. The normal force is a force that opposes equally from things that are touching. So for the box, it's the table is applying a normal force upward. So I could say F sub n, or maybe in your book or the homework, it just has, n or something. If there's a sort of this, for my lecture, I'm going to use F sub n. So that lets you, it sort of reminds you that it's a force pointing upward. So this is like for anything that is touching another thing. So it doesn't have to be vertical. This table sitting on, this box sitting on the table. It could be like me leaning on the wall. The wall is applying a normal force perpendicular to the surface. So I guess I'll write that. A force that is and this is for any two objects, or any objects that are physically touching one another. In this specific example, the normal force is directly upward. I'll do one sort of mini example down here. Say we have a slant. And we have a box that is sort of like just sitting on the slant. It's not moving, but it's, friction is holding it there. I guess I can say that. So gravity, the force of gravity, is making it want to move directly downward. I'm going to instead say force sub g for gravity is directly downward. And the normal force in this example is perpendicular to the surface it's touching. So it's that way, going at an angle. All right, we'll get to maybe a little, maybe some problems like that at the end of this chapter. Okay, a little bit more on free body diagrams. This will be the last slide. So we want to sum up the forces of like a book or something sitting on a table. I'm going to use this box for a physical example. Let's look at the case where the book is not moving. Book or box. I thought I was going to have a book. Instead I have a box. So it's not moving. Okay, so let's draw this free body diagram. So on one end, you can draw more detail. You could draw the table, you could draw the box, the book, or you don't have to. You could just draw, a dot and follow along that way. I'll do this, I'll do that also. So over here, so we have that book, box, whatever, it's at rest. It's not moving. So this diagram is not correct yet. This diagram is showing it's going to go downward. The forces are not canceling each other out so that this object is not moving. So I need that upward normal force. And typically these are drawn to scale, equal size, or just different directions, just to show that they cancel out. let's say for example, I could maybe add a little bit to this. Let's say for example, I can push down on the box, push down more. That's a bigger force downward. But that's also a bigger force upward. They cancel out perfectly. Okay. The box is not moving. If I squeeze it, but in this case, the box is still not moving. So I'm applying forces on both sides. So say for that example, I'm squeezing it. So my one hand is forcing it that way, and the other hand is forcing it that way, but they are equal size and in opposite directions. So they cancel out. Okay, so I'm going to get rid of that so it doesn't look too confusing later on. And again, if you don't want to draw the table and the box or whatever's in your problem, you could do just with a dot. If that makes the problem like much more clear for you to see. There's a force up, there's a force down. Let's look at the case where the book is moving with a constant velocity. Let's use, let's use this. So, based off that previous example, I have this cart. It has mass. It wants to accelerate downward, so it's going to give a force downward. But the table is stopping it from, blowing up this room. So it's going a force down. Table's giving a force up. But what if it's also moving with that constant velocity? Let's say to the right. So we've already decided gravity's forcing it down. The normal force is holding it up. And this is the thing I've sort of said a few times today already. What is a force? A force is, a mass that is accelerating. So, can someone remind me what acceleration means?
Change in velocity per time.
It's a change in velocity. So, if this is moving at a constant speed, does it have a change in velocity?
No.
No, there's no change in velocity when this thing is moving at a constant rate. So, there's no acceleration. And if you remember from that, just put it up one more time. So if there's zero acceleration, there's zero force left or right. So that means that even if something's moving, even this thing is moving, doesn't mean that there is a force in one direction or the other. Okay, and the last one, the book is accelerating to the right. So now, so the book, we got this, track thing. We have this cart, and it starts out slow, and it gets quicker and quicker as it moves to the right. So it is accelerating that way. So you imagine something's constantly pushing it to go faster and faster. So our free body diagram will look like this. So we have to always include those other two forces. It's still sitting on a table. The table is still pushing up on it. But now it has this acceleration in one direction. So it starts out slow, and it gets faster and faster that way. So again, like if you can imagine, I'm just like constantly pushing it and applying a force, making it go faster and faster. There will be, one arrow to the right, and this is not sort of countered by anything because it's accelerating that way. All right. I think that's it. So if you want your quizzes or you have questions on any of this, come down and ask. Otherwise, yeah. Yeah, if you have questions, if you wanted more details on the course, yeah. Homework due Thursday nights. Make sure you remember that. Otherwise, I'll see you guys later.